Hello everyone, my name is Shubham. I am an EEE 236 student at California State University, Sacramento. Today I am going to talk about the integration of 2D materials such as graphene to improve performance and new functionalities in electronics. This presentation will cover various aspects of 2D materials and their integration into electronic devices. The basic outline of the presentation is summarized here. We start with the introduction, then we will discuss why do we look for materials beyond silicon, followed by knowing about graphene and its properties. We will also discuss different synthesis methods used for graphene and graphene's application. Furthermore, we will discuss some challenges in integrating graphene and then know about some materials beyond graphene. Finally, we will conclude key points covered in the presentation and provide references for further reading. We are already heavily dependent on 3D electronic systems. However, researchers have been exploring the possibilities of 2D electronic systems for their unique properties and improved performance. In a 3D semiconductor, such as silicon wafer, electrons can flow through the bulk material in all the three directions. In contrast, in 2D electronic systems, the current is confined to flow in a very thin 2D sheet, leading to improved performance. For instance, the CMOS switches in our computer chips carry current due to electrons that are restricted to flow in a 2D sheet of charge. In this figure, we can see a transistor used in our computer chips that control the current flowing from drain to the source. This is controlled by the voltage applied to the gate. Let's discuss why we want to go beyond silicon. Silicon has been the backbone of electronics industry for decades. Researchers have consistently kept pace with Moore's law, which states that the number of circuits on a microchip doubles every 2 years. They have accomplished this by experimenting with variations of semiconductor materials. However, geometric scaling will eventually reach its limit as chips approach atomic levels of scale. A look at data from 1970s illustrates these exponential performance improvements. However, in recent years, the pace has slowed considerably. PC processing power has leveled off and increases in smartphone processor performance have begun to slow. We can clearly see these things in the above two graphs. Secondly, we have the issue of rising production cost. Manufacturing instrument cost has increased since the industry made the transition to multi-patterning. This has resulted in significant R&D investment for leading node technology. Moreover, there are also physical limitations of silicon. For example, node length is approaching the conducting channel width, inhibiting the transistor performance. There are also limitations in lithography, instrumentation, and fabricating a nano-sized structure. All of these factors have contributed to the need to explore beyond silicon and find alternative materials that can overcome these limitations. This is where graphene, a 2D material, comes in as a promising candidate. Let's know about graphene. Graphene was discovered in 2004 by Andrei Jim and Konstantin Novoselov. We can take an example of common pencil shown in the figure. The lid of a pencil is graphite. If I took the microscopic view of this pencil trace, this gives us the idea that graphite consists of multiple crystals which are easy to slide. If we are able to zoom into these crystals, we will be able to see the number of one atom thick carbon layers. In 2004, these two folks were able to isolate a single sheet of carbon layer from graphite, and only 6 short years later, it won the Nobel Prize in Physics. So, graphene is a one atom thick layer of carbon atoms arranged in a hexagonal lattice. Moving to the next slide, graphene has a set of unique optical, mechanical, and electrical properties. Here I'm going to discuss few of them. First, It is nearly transparent as a single layer, which makes it suitable for many optoelectronic applications. Second, it has almost 300 times higher strength than steel, which is very useful in aerospace and defense applications. Third, due to its unique electronic structure, it has ability to conduct electricity with very low resistance, leading to minimum energy loss in electronic devices. Additionally, it has high thermal conductivity. This property is attributed to the strong covalent bonding between its carbon atom, which allows heat to be efficiently transferred through the material. Also, the zero band gap in graphene attributed to the higher electron mobility. Let's move on to some of the synthesis methods used for graphene. Mechanical exfoliation. The first monolayer of graphene was obtained by this method. The technique involves using a small piece of adhesive tape to press onto a bulk material, such as graphite, and then peeling off the tape. During the peeling process, layers of material are separated and transferred onto a substrate. This process is repeated several times to obtain thinner layers of graphene. The other method for synthesis is liquid phase exfoliation. It is a solution-based method that can yield a large volume of 2D nanoseed in a cost-effective way. The process begins by soaking a bulk crystal in a specific solvent. The mixture is then subjected to ultrasonic waves through a process called sonication to break up the bulk material by applying mechanical energy. This results in a homogeneous solution containing a high concentration of 2D nanoseeds. Next, chemical vapor deposition is a popular method for synthesizing large area, high quality graphene films. In this process, a carbon containing gas is introduced into a high temperature furnace where it reacts with a metal catalyst to form graphene on a substrate. Now that we have discussed the integration methods for graphene, let's explore some of its exciting applications. In the electronics industry, graphene has shown promise as a flexible material for building transistors. Its capability to operate at low voltage with high sensitivity at room temperature makes it better than a silicon transistor. It has also been used in lithium-sulfur batteries to improve their performance. The addition of graphene to the battery's cathode can help to prevent the loss of sulfur and improve the overall energy efficiency of the battery. In the optoelectronics industry, graphene has been used to create photodetectors, solar cells that are highly sensitive to the light. Its ability to absorb light across the broad spectrum makes it ideal for use in imaging and sensing applications. It has also been used in coatings and energy storage applications. Here are the future prospects or phases for graphene adoption by some experts. Is a prediction. In the near term, we expect graphene to be used as an enhancer for silicon, with protective layers of graphene used to improve the reliability and performance of interconnects. Over the next 10 to 25 years, graphene could replace silicon as the primary material in semiconductors, assuming research discovers method to overcome its band gap limitation. Lastly, we will be able to make one layer lithography a reality. Interestingly, all these phases have made some headway. We have already seen the revolutionizing applications of graphene in the field of electronics. However, there are several challenges that must be overcome before it can become a widely adopted material in the industry. One of the major challenges is the high cost of producing graphene at large scale. Another challenge is the lack of bandgap in graphene. This means it cannot be used to make traditional transistors, which require a bandgap to turn off the current flow. Next is the compatibility of graphene crystals with CMOS devices. While graphene has excellent electrical properties, is compatibility with existing CMOS fabrication processes need to be explored and optimized. Coating and transferring procedures are also a challenge with graphene. Currently, the tools and processes for graphene transfer are developing. Next, the current quality control process for graphene is too slow for large-scale industry-related applications. Finally, there is also the risk of unknown hurdles in the process of incorporating graphene into electronic devices. Despite these challenges, with further research and development, graphene could become a key material in the next generation of electronic devices. All this excitement about 2D graphene led people to look for other 2D materials which have unique properties. I am going to discuss a few of them here. One such class of materials is transitional metal dichalcogenides or TMDs. These materials have a direct band gap. Another interesting class of 2D materials is topological insulators or TIs. These materials behave as insulator in the bulk but have good metallic conductivity at their surface. There are also 2D non-noble metals like 2D gallium and 2D indium. Also, there is a material, black phosphorus, which is semiconductor and has a tunable band gap. As we have seen, 2D electronic systems have been around for decades and are only growing in importance. Graphene extraction was a kind of eye-opening experience for researchers and spurred research on other 2D materials. The unique electronic and optoelectronic properties of 2D materials, along with their tunable bandgap, have enormous potential to improve the performance and functionality of electronics, which has been made possible by advancements in material integration and fabrication techniques. The potential application of 2D materials in various industries, including healthcare, energy, and communications, are vast and exciting. However, as research on 2D materials continues to progress, it is essential to address the challenges in terms of scalability and cost effectiveness to make these materials commercially viable. Here is the list of references. Thank you for watching.